Hello there. This is Miss Page, and this lesson is going to be on finding the volume of a cone, or solving problems involving the volume of a cone. So our formula for calculating volume of a cone is actually similar, the same structure as our formula for finding the volume of a pyramid, which we spoke about in the previous lesson. So we have 1/3 times our base area, capital B, times the height of the cone. Because in a cone, the base is always a circle, that base area has to be our area of a circle formula anytime we're doing volume of a cone, and that is our pi r squared. So our capital B in a cone will always become our pi r squared. The other thing we have to be super careful of and realize for a cone is that, remember, h is the height of the cone, and we've been talking a lot about the fact that the height of the cone is, or the height of any solid, is perpendicular to its base. So we always look for that right angle. So here you see in this diagram, here's our right angle. So perpendicular would be this measurement going up to the apex of the cone. So this is what we have to make sure that we use for the h portion of this formula. Our radius is here. That's the radius of it. And then notice we also have a different type of height here that is called slant height. And we use a cursive L to represent slant height. And it goes from the apex down to the outside edge or circumference of the circle. You might also realize that the height h of the cone, the radius of the circular base, and the slant height of the cone form a right triangle. So in cone problems, we often have to use our Pythagorean theorem to find either the height h of the cone or the radius r of the circular base. All right, let's take a look at our first example. So here it says a topiary tree is shaped into a cone with a diameter of 5.9 feet and a slant height of 6.3 feet. What is the volume of the topiary tree is our question. So that's pretty straightforward, just calculating a volume. And our topiary tree, we're told, is in the shape of a cone, which means we're calculating volume of a cone. If you are not familiar with the word topiary, topiary is a word that's used to describe a very dense bush or tree that can be shaped by pruning into some sort of figure or object. This one is just shaped into a simple cone. If you've ever been to Disneyland, they have a lot of topiaries that have been shaped into characters and animals and stuff like that. Those are other types of topiaries. With our topiary that's shaped like a cone, we are told that it has a diameter of 5.9 feet and that it has a slant height of 6.3 feet. So we need to realize that slant height there, that is our L, not our H, because of the word slant. So if you want to, you can draw a new diagram to actually label stuff. So you can draw a cone by almost drawing a triangle, but at the bottom, curving it to look like a circle. So what this is telling us is that our diameter, remember diameter goes all the way across the middle of the circle, like so. That's our diameter, which is 5.9 feet. And we have a slant height, which would be on the slanted edge from the apex down to the circumference of the circle here. That's our L, slant height of 6.3 feet. Our volume formula for a cone, which we were just talking about, which starts off as 1/3 times base area times the height of the cone. Our base area, remember, is area of a circle, so that becomes pi r squared. So our volume formula becomes 1/3 times pi r squared times the height h of the cone, which means that we need the values or quantities, the measurements, for our radius r and our height h, neither one of which do we know at this point. One of the things that we need to realize is that we're actually going to have to find our radius first, because if you recall in this diagram, the right triangle that involves our height h also involves the radius r, not the diameter. So we actually need r first before we can find our height here. So first thing I'm going to do is find the radius. And we know that the radius is half of the diameter. So I'm going to take my diameter and divide by 2. And dividing that by 2 is going to give us 2.95 feet. So that's our radius, or r value. So now I can actually move on to height. And for height h, I am going to draw the right triangle that it is part of. So remember, the height h drops perpendicular down here from the apex to the middle of the base. That's my height h. So this right triangle is what I'm going to work with. So I have to realize that that right triangle that this leg over here, my vertical leg, that's my height h, that the leg down here, the horizontal leg, that's my radius r, and then the hypotenuse of my right triangle will always be my slant height L. So I know now I was given the slant height, which is 6.3 feet, and I've calculated my radius, which is 2.9 feet, or 2.95 feet. So now I can apply my Pythagorean theorem to my right triangle. So I have a squared plus b squared equals c squared. And remember that the c value has to be the hypotenuse, which will always be our slant height in this case. So that's our 6.3. Which a or b using h or our r value doesn't matter because it's a sum. So I'm going to write h squared plus 2.95 squared equals 6.3 squared. Now I could do the math with a calculator, say here, and figure out these decimals and then do my subtraction, but it's generally a little bit faster and requires less writing if I subtract 2.95 squared from both sides and do the algebra all here with these squared decimals and use my calculator at the end. So I'm going to do it that way. So I'm going to subtract the 2.95 squared from both sides. So now I have h squared equals 6.3 squared minus 2.95 squared. And then I'm going to undo my exponent of 2 using my square root property. So take the square root of h squared. And here, remember, we'd only need the principal square root, because that's the positive square root, because h is a measurement and needs to be positive. So that's the square root of 6.3 squared minus 2.95 squared. So our square and square root will cancel each other out over here, and that gives us h. And now I'm going to use my calculator on this and figure out an approximation for this. When I do, remember, best practice will be to carry it out a couple of extra places beyond the tenths, because I don't want to round to the tenths for accuracy until the very, very end of the problem. So I'm going to carry it out to the third decimal place, or the thousandths place. Alright, so carrying this out, this calculation, one of the things you want to remember for using your calculator is that your radicand, what you're taking the square root of, should be in parentheses, and then you should be good to go. And you should be getting here about 5.567. The units on our height would have to be the same units as our slant height and our radius, which are both in feet. So we get a feet measurement here. So now we know radius and we know our height h. So now we are ready to calculate the volume of our cone, which is also our topiary tree in this case. So our volume again is 1/3 times our base area, which is our circle area, pi r squared, times our height h. So, plugging in our values now for r and for h, our volume is going to become 1/3 times pi times 2.95 feet, quantity squared, times our height of about 5.567 feet. Again, I am not going to figure this out separately, this 2.95 squared. Remember, we are squaring the 2.95 as well as the feet. So in my calculator, because I've got these rather extended decimals, what I'm going to do is pi times my 2.95 squared times my 5.567, and then I'll divide by 3 for my times 1/3. Alright, so if you've done the calculation correctly, this is going to give us about, to the nearest tenth now is where I'd round. That's my rounding instructions for the end of the problem. So about 50.7. And my units come from my feet squared times feet, which gives me cubic feet, which makes sense for a volume unit. So now all that remains is my conclusion. So the volume of the topiary tree is about 50.7 cubic feet. Alright, we are now going to look at the next problem, which is a practice problem. Alright, there you go. Give that one a try. Alright, and had some time now to finish this practice problem. Here is the result. You should have determined that the volume of the hut is about 1005.3 cubic feet. There's another practice problem here for you to try. Pause the video if you would. Alright, now that you've had some time, go ahead and take a look at the results. So here you should have determined that the glass will hold about 11.3 fluid ounces. Now we're going to go on to the next example. Alright, so let's take a look at this first part here. This one is going to be about a composite figure situation that involves a cone. So here we have the roof of a grain silo is in the shape of a cone. Grain silo, if you're not familiar with that term, here's an example of one. And it's a very large structure that holds different types of grain like wheat, rice, all kinds of stuff. So the roof is in the shape of a cone. And it tells us that the inside radius of that cone is 20 feet and that the roof has a height of 10 feet. It's 10 feet tall. Below that cone, we can see here in the picture, is a cylinder. And that cylinder is 30 feet tall, but it has the same radius as the roof, which is the cone. And we will be looking at finding the volume of the silo, and we'll do so to the nearest tenth. So we need to realize, okay, well, we actually have a composite here. The volume of our silo would be equal to the volume of the cone, which is the roof, plus the volume of the bottom portion, which is a cylinder. And our cone formula for volume is 1/3 times base area times height. We'd add that to our volume formula for our cylinder, which is just base area times height. Since both the cone and a cylinder have bases that are shaped like circles, the base area for each of them is the area of the circle formula, which is pi r squared. So this then becomes 1/3 times pi r squared times h plus pi r squared times h. Now, in the next step in which we're going to figure out our numbers to use for r and h, we do want to make sure we're careful about making sure that we use the radius and height for the cone in this part and the radius and the height for the cylinder in this part. Otherwise, we won't get the right answer. So what I'm looking at here then is understanding. So I've got 1/3 times pi. My radius for the cone, which is the roof, is 20 feet. So that'll be 20 feet squared times the height of the roof, which is 10 feet. And then I'm going to add that to pi times the radius squared for the cylinder bottom. And it, we're told, has the same radius, so we'll again use our 20 feet here and square that. Now we multiply times the height of the cylinder portion. That's a different height. That, we're told, is 30 feet. So we would put a 30 feet in for this h. Now you could, as long as you practice best practices with rounding, things like that, you could find these volumes individually and then add them together, but this is a little more efficient. We are now just going to go through and let our calculators do all of this calculation. So remember, here we're squaring the 20 as well as the feet, and here also. So in my calculator, I'm going to do pi times 20 squared times 10, then divide that by 3, and then I'll hit the plus key and hit pi key times 20 squared times 30, and then I'll hit my equals, and then I will round that final answer to the nearest tenth, and that will give me my volume for the silo, the most accurate volume to the nearest tenth. So let's use our calculators. All right, so hopefully you came up with this number, 41,887.9 to the nearest tenth. And our units would be our feet squared times feet, which is cubic feet. So now we can write our conclusion. We have this would be our volume of our silo. So the volume of the silo is about 41,887.9 cubic feet. All right, so now it's time for us to take a look at this part B. So part B here, it says we have a farmer's crop, and it consists of approximately 2 million pounds of wheat. If 1 cubic foot of wheat, so if 1 cubic foot of wheat is approximately 48 pounds, will all of the wheat fit in the silo? And explain our reasoning. So give justification for why we are going to say yes or no. And that justification should involve some math calculations that we do here. All right, so we know that the crop for the farmer is approximately 2 million pounds. We know that 1 cubic foot, which if you'll notice is our units for our volume, and that 1 cubic foot of wheat is about 48 pounds. So what we can do here is take our volume of cubic feet and convert it into pounds and figure out if there will be enough space for all of the pounds of the crop. All right, so we take our volume of 41,887.9 cubic feet, which has a denominator of 1. And our conversion ratio, we have to realize this is a conversion ratio. 1 cubic foot equals about 48 pounds. So we put our 1 cubic foot here. So our cubic feet will cancel, and our 48 pounds would go here. And then our answer is going to be converted into pounds, and we can do a comparison. So our cubic feet go. We need to take our volume times our 48 and figure out what that is equal to. All right, so hopefully you came up with this number. I have 2,010,000 619.2. And now my units are in pounds. So now I can do a comparison. So this, remember, is my silo. This is what fits in the silo. And this is what the farmer wants to put in the silo, approximately 2 million pounds of wheat. So, since this number here is larger than 2 million, not much, but it is larger, the farmer should be able to fit all of the wheat in the silo. So, we can write a conclusion based on that comparison. So, will all the wheat fit in the silo? All of the wheat will fit in the silo. Here, that's our conclusion, and then we have to justify that using mathematical reasoning here. So, because about 2,010,000 pounds, I'm just rounding, you could use this entire amount, I'm just rounding, but this will be enough, pounds will fit, and the farmer has less than that amount. Or another way you could word it is that the silo will fit about 10,000 pounds more than the 2 million pounds of wheat the farmer needs to put in the silo. So, several different ways that you can justify that conclusion. All right, so let's try a practice problem here. So you can pause the video, give this one a try. All right. So, if you have completed this practice problem, you take a look at the results here. So, for the first part, you hopefully concluded that the volume of the post is about 4.1 cubic feet. And here, the number of pounds of concrete for 6 posts, so we have to make sure we do multiply by 6, is about 3,695.7 pounds will be needed of concrete. All right. So now we have another example. Let's take a look at this one. So here it says Karen removed a cone shape. And she removed that cone shape from a metal cylinder. They tell us that the apex or tip of the cone is at the base or bottom of the cylinder. We are to find the volume of the remaining metal. So we have this metal cylinder, and some sort of tool was used to take out a cone shape from inside the cylinder. So we've seen a problem like this before, where it's similar to a composite, but because we have a part being removed, we're going to need to subtract off that volume of what's being removed rather than add it to. So we are looking here, the volume of the remaining metal would be the volume of the cylinder, which is the larger figure, minus the volume of the cone that is removed. So our cylinder is base area times height for volume. Our cone is 1/3 times base area times height. Both of them do have a base shape of a circle. So that area formula is pi r squared. So we have pi r squared h minus 1/3 pi r squared h. So again, similar to the silo problem, we want to make sure that we use the correct numbers for the radius and the height for the cylinder and the cone. In this case, This arrow here that's pointing to kind of this dot means that it's talking about this entire line segment from beginning to end. So we have to realize that is our diameter. And that is the same circle as what's up here. And this is the base of our cone. This is the base of our cylinder. So they're going to have the same diameter. They're also then going to have the same radius. So my radius would be half of that diameter, or 3.6 centimeters divided by 2. So this is going to give us a radius of 1.8 centimeters. The other thing that we need, and they'll have the same radius, the other thing that we need is the height of each of them. Well, we can see that the cone starts and stops at the bottom and top of the cylinder, so they're going to have the same height too. The height of the cone would be like from here to here, perpendicular. That's going to be this measurement because they are parallel to each other. So this is the height of both the cone and the cylinder. So it's the height of the cone and it's the height of the cylinder. So we plug in our numbers and we have pi times the radius of the cylinder, which is 1.8 centimeters. We square that, times the height of the cylinder, which is 4.3 centimeters. Then we're going to subtract the volume of the cone. So we have 1/3 times pi times the radius, which is again 1.8 centimeters, and that's squared, times the height, which is again 4.3 centimeters. So again, I would just let my calculator do all of this and save myself some time and some writing. So I would do pi times 1.8 squared times 4.3 in my calculator, and then I just keep on typing. I'd hit my subtraction key, and then I would hit pi times 1.8 squared times 4.3 divided by 3 for the times 1/3, and then I hit equals. And now is when I will round to the nearest tenth. Alright, so hopefully you got the same number as I did, and to the nearest tenth it's about 29.2. Our units, we have centimeters squared, remember, times centimeters, plus centimeters squared times centimeters. That's cubic centimeters minus cubic centimeters, which means that we are in cubic centimeters. So now our conclusion here is we were finding the volume of the remaining metal. So the volume of the remaining metal is about 29.2 cubic centimeters. All right, so next there's a practice problem. You can give this one a try. All right, if you have finished your practice problem, I'm going to reveal the result here. So we had to realize we had our cylinder and we were actually removing 2 cones. The cone here and the cone here. Here the heights were not the same. Hopefully you realize that the height of each of the cones individually was 6 inches, half of the 12 inches for the cylinder. So we ended up with the volume of the cylinder here minus the volume of the cone twice, or you could multiply the volume of the cone times 2 and then subtract that number. Either way, hopefully you got to the nearest hundredth, about 904.78 cubic inches. All right, and here's your closure. It says the volume for both a cone and square pyramid are the same here, 1/3 times base area times height, where B is the base area. Explain how the base area is different for a cone and a square pyramid. So hopefully you realize that this is asking us to recognize that the shapes are different, therefore the formula that we're going to use for base area is different. So in a cone, we have a circle, so we would use pi r squared for capital B. But in a square pyramid, our base is the square, so we'd use s squared for our capital B. All right, and that finishes this lesson.